Hello there. I'm so glad you found your way here tonight. Right now, as you settle in, countless worlds are spinning silently through the darkness of space. Some orbit familiar suns. Others drift alone through the endless void, untethered to any star at all. Beyond our solar system, we have discovered thousands of planets circling distant stars. Worlds where metal rains from burning skies. Planets made almost entirely of diamond. Oceans so deep they have no floor. Giants larger than Jupiter, and rocky worlds that may be more habitable than our own. Tonight, we embark on a tranquil journey through these distant realms. We will drift through over 100 soothing facts about exoplanets, the strange and beautiful worlds that orbit stars beyond our sun. There is no test at the end. No rush. No urgency. Just the gentle unfolding of the universe's most extraordinary secrets to carry you softly towards sleep. So let your breathing slow. Let your thoughts wander outward past the familiar sky. And allow yourself to drift peacefully into the quiet wonder of worlds we have only just begun to discover. Welcome to Drowsy Discovery. I am glad you found your way here tonight. Perhaps you have had a long day. Perhaps you simply enjoy falling asleep to thoughts about the vast and mysterious cosmos beyond our solar system. Either way, this space is for you. There is something deeply calming about contemplating distant worlds. Every planet we discover carries within it a story billions of years in the making. Some are born from the same spinning disk of dust that created their star. Others are captured wanderers, pulled into orbit after drifting through the galaxy alone. You are connected to this story. The atoms in your body were forged in ancient stars that may have hosted their own planets. The iron in your blood, the calcium in your bones, the oxygen you breathe, all of it once drifted through interstellar space, perhaps passing by worlds we will never see. If you enjoy these gentle journeys, I invite you to like, subscribe, or share a thought below. It helps others find their way here too, one sleepy soul at a time. But for now, all you need to do is relax. So, settle in. Let the weight of the day drift away like stardust scattered by the solar wind. And let us begin with the first of many peaceful truths about planets beyond our sun. The universe is patient beyond measure. Stars burn for billions of years. Planets orbit in cycles that span millennia. And somewhere out there, worlds we cannot yet imagine are quietly turning, waiting to be discovered. Tonight, we will wander through this magnificent cosmos. We will meet planets hotter than stars and colder than deep space. We will discover worlds with twin sunsets and others that glow with borrowed light. And we will uncover truths about exoplanets that may surprise even the most curious minds. But there is no hurry. The planets have been orbiting for billions of years. They can wait a little longer while you rest. Let us begin with the most extreme worlds. Some planets reach temperatures hotter than many stars. Among the most extreme worlds we have discovered are the ultra-hot Jupiters, gas giants that orbit so close to their stars that their atmospheres glow, with temperatures exceeding those of some red dwarf stars. The hottest exoplanet ever measured, Kelta 9b, reaches temperatures above 4,000 degrees Celsius on its day side, hotter than many stars in our galaxy. At these temperatures, hydrogen molecules are torn apart into individual atoms, and heavy metals like iron and titanium exist as vapor drifting through the atmosphere. These worlds challenge our understanding of what a planet can be, existing in a realm between familiar gas giants and the stellar objects they orbit. The extreme heat drives powerful winds that redistribute energy around the planet, creating weather patterns unlike anything in our solar system. Ultra-hot Jupiters are laboratories for studying physics at temperatures that would vaporize almost any material we know. They remind us that the universe creates worlds at the very edge of what is possible. Hot Jupiters orbit so close to their stars that their atmospheres boil away. When a gas giant orbits mere millions of kilometers from its star, the intense radiation begins to strip away its atmosphere layer by layer. This process, called atmospheric escape, has been observed on several exoplanets, with hydrogen and helium streaming away like a comet's tail. Some hot Jupiters are losing millions of tons of atmosphere every second, yet their immense mass means they can survive for billions of years before being significantly diminished. The escaping gases form extended envelopes around the planet, detectable when the planet transits in front of its star, and the starlight passes through this diffuse material. Over time, atmospheric escape may transform some hot Jupiters into bare rocky cores, stripping away their gaseous layers to reveal the solid heart beneath. The process offers a glimpse into the violent relationship between close-orbiting planets and their parent stars. These worlds are slowly evaporating, sacrificing themselves to the relentless heat of their suns. On some worlds, the dayside temperature can vaporize iron. The dayside of the hottest exoplanets is a realm where familiar substances behave in unfamiliar ways. Iron, which requires temperatures above 2,800 degrees Celsius to vaporize on Earth, exists as a gas in the atmospheres of ultra-hot Jupiters. This iron vapor drifts through the air, carried by powerful winds toward the cooler night side, where it may condense and fall as metallic rain. Titanium, vanadium, and other refractory metals similarly vaporize on the dayside, creating atmospheres with chemistry unlike anything in our solar system. The transition from day to night on these worlds involves dramatic changes in state, with metals that are gaseous on one side becoming liquid or solid on the other. Spectroscopic observations have confirmed the presence of iron vapor in the atmospheres of several ultra-hot Jupiters, allowing scientists to study these extreme conditions from light years away. These worlds are forges where the familiar boundaries between solid, liquid, and gas are rewritten by extreme heat. Certain planets are so hot that molecules break apart in their atmospheres. At the temperatures found on ultra-hot Jupiters, the chemical bonds that hold molecules together cannot survive. Water vapor, which might exist on the cooler night side, is torn apart into hydrogen and oxygen atoms on the scorching day side. Even hydrogen molecules, the simplest and most stable diatomic molecules, are split into individual atoms at temperatures above 2,000 degrees Celsius. This molecular dissociation has profound effects on the planet's atmospheric structure and heat transport. The energy required to break these bonds absorbs heat on the day side, while recombination on the night side releases that energy, creating a kind of molecular heat pump. Scientists have observed this phenomenon on WASP-76b and WASP-121b, using spectra that reveal the transition from molecules to atoms as we observe different regions of the planet. The chemistry of these atmospheres is dynamic and violent, with molecules constantly being destroyed and reformed as gases circulate around the planet. Some ultra-hot Jupiters blur the boundary between planet and star. The hottest exoplanets challenge our definitions of what separates a planet from a star. Brown dwarfs, objects that bridge the gap between the largest planets and the smallest stars, generate some heat through gravitational contraction, but lack the mass to sustain hydrogen fusion. Some ultra-hot Jupiters approach or exceed the temperatures of cool brown dwarfs, yet they shine with reflected and re-emitted light rather than internal fusion. The boundary is further blurred by objects like Kelt 9b, which receives so much radiation from its nearby star that its atmosphere resembles a stellar photosphere more than a planetary one. These objects force astronomers to reconsider the categories we use to organize the universe. A planet heated to stellar temperatures is still a planet by formation and mass, but its behavior mimics that of a star. The universe delights in creating objects that defy our neat classifications, reminding us that nature is more creative than our categories. Some exoplanets might be made almost entirely of diamond. In star systems where carbon is more abundant than oxygen, planets may form with a completely different chemistry than the silicate worlds of our solar system. These carbon planets would have mantles of diamond and graphite instead of the rock and metal that make up Earth's interior. The immense pressures deep inside such worlds would compress carbon into diamond on a planetary scale, creating gems that dwarf anything on Earth by many orders of magnitude. Scientists believe that some super-Earths orbiting carbon-rich stars could be genuine diamond worlds, glittering with crystalline structures throughout their interiors. The surface geology of such planets would be utterly alien, with graphite continents and possibly hydrocarbon oceans. While we have not yet confirmed the existence of a diamond planet, the chemical diversity of the galaxy makes their existence plausible, if not likely. These hypothetical worlds remind us that the building blocks of planets are determined by the stars that birthed them. Carbon-rich planets could have mountains of graphite and seas of tar. On worlds where carbon dominates the planetary chemistry, the landscapes would look nothing like anything on Earth. Mountains might be formed of graphite, the soft black mineral that forms pencil leads, rising against skies tinged with organic haze. Valleys could hold lakes or seas of liquid hydrocarbons, thick tar-like substances that flow slowly under alien suns. The atmosphere might be rich in methane, ethane, and other carbon compounds, creating a smog that filters the light into eerie hues. Rivers of petroleum might carve channels through graphite bedrock, depositing strange sediments in deltas of frozen hydrocarbons. These carbon worlds would smell of oil and smoke, their surfaces slick with the chemical precursors of life. While hostile to human exploration, carbon planets would offer chemistries that do not exist on any world in our solar system. They represent an entirely different branch of planetary evolution, one written in carbon rather than silicon and oxygen. Some worlds may have ruby and sapphire clouds drifting through their skies. The atmospheres of certain hot exoplanets contain temperatures and pressures that allow aluminum oxide, the mineral that forms rubies and sapphires, to condense into clouds. These gemstone clouds would drift through alien skies, their crystals catching and scattering light in spectacular displays. On planets like Hatat P7b, observations suggest that corundum clouds may form on the night side, where temperatures drop enough for condensation. The clouds would shimmer with the deep reds and blues we associate with precious gems, though no human eye may ever witness them directly. As these clouds circulate from night side to day side, they may evaporate in the intense heat, only to reform again as gases cool. The presence of such exotic cloud types was predicted by atmospheric models, and has been supported by observations of changing brightness patterns. The universe decorates its worlds with materials we treasure, though on scales and in contexts we can barely imagine. Certain planets are darker than charcoal, absorbing nearly all light. Among the strangest exoplanets discovered, are those that reflect almost no light at all, appearing darker than coal or fresh asphalt. TRES 2b, sometimes called the dark planet, reflects less than 1% of the light that strikes it, making it one of the darkest objects ever observed. Scientists believe the extreme heat of such planets prevents reflective clouds from forming, while sodium, potassium, and other alkali metals in the atmosphere absorb light across the visible spectrum. The result is a world that appears almost black against the backdrop of space, visible only by the faint infrared glow of its own heat. These dark planets challenge our assumptions about what worlds should look like, existing as cosmic shadows orbiting their stars. Their darkness makes them difficult to study with reflected light, requiring infrared observations to pierce their mystery. The dark planets are reminders that the universe contains worlds that hide themselves in shadow. Some exoplanets are so lightweight they could float in water. Astronomers have discovered a class of exoplanets with densities so low that they would float if placed in a cosmic bathtub large enough to hold them. These puffy planets, often called superpuffs or cotton candy planets, have masses similar to Neptune but radii several times larger, giving them densities less than that of water. The source of their extreme puffiness remains debated, with theories ranging from extended hydrogen atmospheres to obscuring rings or hazes that make the planets appear larger than they truly are. Kepler-51 hosts several of these inflated worlds, each with densities comparable to styrofoam. How such low-density atmospheres remain bound to the planet is an active area of research, as the weak gravity should allow gases to escape rapidly. These cotton candy planets may represent a transitional phase, slowly losing their extended atmospheres to become denser worlds over time. They demonstrate that planetary density can vary far more than our solar system would suggest. Other worlds are dense enough to crush iron at their cores. At the opposite extreme from the puffy planets are worlds so dense that their cores experience pressures unlike anything found in our solar system. Super-Earths with masses many times that of our planet compress their interiors to extraordinary degrees, creating conditions where iron and other heavy elements are squeezed into exotic high-pressure phases. The cores of the densest rocky exoplanets may reach pressures of tens of millions of atmospheres, forcing atoms into configurations that do not exist naturally on Earth. At such pressures, the behavior of matter becomes strange, with materials becoming metallic or crystalline in ways that laboratory experiments can only briefly approximate. The gravity on the surface of such dense worlds would be crushing to human visitors, with objects weighing several times what they would on Earth. These dense planets are natural laboratories for studying extreme physics, their interiors recreating conditions found in the hearts of much larger worlds. They represent the ultimate compression of rocky material, planets packed as tightly as physics allows. Some exoplanets may be covered in oceans thousands of miles deep. Among the most intriguing worlds we have discovered are the water worlds, planets where liquid water forms global oceans that may extend hundreds or even thousands of kilometers beneath the surface. These worlds likely formed beyond the snow line of their star systems, where water ice was abundant during planetary formation, before migrating inward to warmer orbits. The oceans on such planets would be so deep that no sea floor exists in the traditional sense, with water eventually compressing into exotic high-pressure ice phases at depth. The weight of so much water would create pressures millions of times greater than Earth's sea level at the deepest points. Life in such oceans, if it exists, would have to adapt to a world without solid ground, existing in an endless liquid realm. Water worlds may be common throughout the galaxy, representing a category of planet that does not exist in our solar system. These drowned worlds remind us that water, the molecule essential to life as we know it, can dominate entire planets. Ocean worlds might have no continents or islands at all. On planets with enough water, the geological processes that create dry land on Earth may never occur. Continental drift requires a balance between ocean volume and crustal thickness that may not exist on worlds with too much water. Without continents to erode, the ocean chemistry on these worlds would be fundamentally different from Earth's, lacking the mineral inputs that terrestrial weathering provides. The absence of land would mean no beaches, no mountains rising above the waves, no place where the sea meets the sky in visible form. Any life on such worlds would be entirely aquatic, never evolving the adaptations that allowed Earth's creatures to crawl onto land. The climate of continentless worlds would be more uniform, without the land masses that create deserts, monsoons, and seasonal variations. These true ocean worlds would be serene and featureless from space, blue spheres unbroken by the brown and green of dry ground. Deep beneath alien oceans, exotic forms of ice could behave like rock. At extreme pressures found deep within massive water worlds, ice takes on forms that do not exist naturally on Earth. Ice 7, which requires pressures over 10,000 times Earth's atmospheric pressure, forms a dense crystalline structure that sinks rather than floats. At even greater pressures, Ice X forms, with hydrogen atoms arranged in a perfectly symmetric lattice. These exotic ices would form mantles around the rocky cores of water worlds, creating layers of solid water hundreds of kilometers thick. The behavior of these high-pressure ices influences how heat escapes from the planetary interior and whether life-essential chemicals can cycle between the ocean and the core. In some models, the ice mantle acts as an insulating barrier, trapping geothermal heat and creating warm pockets at the ice-ocean boundary. The physics of water at extreme pressures continues to be studied in laboratories, revealing behaviors that help us understand distant worlds. Ice that acts like rock is just one of the many wonders hidden in the depths of alien oceans. Some planets may be shrouded in thick layers of steam. Between the ice giants and the water worlds exist planets where temperatures and pressures create global steam atmospheres thousands of kilometers thick. These steam worlds would have no clear boundary between atmosphere and ocean, the water transitioning smoothly from gas to supercritical fluid to liquid with increasing depth. The supercritical region, where water has properties of both liquid and gas, would be unlike any environment on Earth, a realm of strange chemistry and physics. Light penetrating such an atmosphere would scatter and dim rapidly, plunging the deeper layers into perpetual twilight. The greenhouse effect of a thick steam atmosphere would trap heat intensely, potentially creating runaway warming that prevents the water from condensing into stable oceans. Venus may have experienced a similar fate early in its history, losing its water to space after steam in the upper atmosphere was broken apart by sunlight. Steam worlds represent a transitional state, balanced between the water worlds and the hellish greenhouse planets. Subsurface oceans might exist on planets far from their stars. Even planets that receive little or no starlight might harbor liquid water beneath insulating crusts of ice. This scenario, familiar from the moons of our own solar system like Europa and Enceladus, could apply to exoplanets orbiting at great distances from their stars, or even to rogue planets drifting through interstellar space. The heat needed to maintain liquid water could come from radioactive decay in the planet's interior, or from tidal forces if moons or companion worlds provide gravitational flexing. These subsurface oceans would be isolated from the surface by kilometers of ice, existing in perpetual darkness but potentially warmed by hydrothermal vents on the ocean floor. Life in such environments would depend entirely on chemical energy, never knowing the light of any sun. The possibility of subsurface oceans vastly expands the potential habitable real estate in the galaxy, as distance from a star no longer determines whether liquid water can exist. hidden oceans may be far more common than surface seas in the cosmic census of water. Some exoplanets orbit two suns, creating twin sunsets. The science fiction dream of a world with two suns in the sky has become scientific reality with the discovery of circumbinary planets. Kepler-16b was the first confirmed planet orbiting a binary star system, forever changing our understanding of where planets can form. From the surface of such a world, two suns would rise and set at different times, creating complex patterns of light and shadow that change throughout the orbital period. The colors of the two stars might differ, one perhaps orange or red, while the other shines yellow or white, painting the sky in hues impossible on single-star worlds. The gravitational dance of two stars creates a dynamic environment where the planet must find a stable orbit that avoids being torn apart or ejected. Despite these challenges, circumbinary planets have proven to be surprisingly common, with dozens now confirmed. These twin-sun worlds bring the impossible visions of cinema into the realm of scientific fact. Circumbinary planets move in beautiful, complex loops around pairs of stars. The orbital mechanics of a planet around two stars are far more complex than the simple ellipses of single-star systems. As the two stars orbit their common center of mass, the planet must weave around both, tracing a path that resembles a spirograph pattern when viewed from above. The planet's distance from each star constantly changes, creating seasons driven not just by axial tilt, but by the varying intensity of light from each sun. Computer simulations show that stable orbits are possible only at certain distances, creating zones where planets can survive, and others where gravitational chaos would tear them apart. The planets that do survive in circumbinary orbits often lie near the edge of this stability limit, dancing on the boundary between order and chaos. The discovery of these worlds required new methods of analysis, as the transit signals were complicated by the motion of both stars. Circumbinary planets demonstrate that planetary formation is robust enough to succeed, even in gravitationally challenging environments. Planets have been found in star systems with 3 or more suns. Beyond binary systems, astronomers have discovered planets in systems where 3, 4, or even more stars share the gravitational stage. The planet HD 131399a flat orbits in a system with 3 stars, experiencing triple sunrises and sunsets, depending on the orbital configuration. In the most extreme cases, planets may see different numbers of suns at different points in their orbits, with some suns appearing close and bright, while others are distant specks. The stability of planets in such systems is remarkable, as the gravitational influences of multiple stars would seem to preclude long-term survival. Yet nature has found ways to tuck planets into stable niches within these complex stellar dances. Some planets orbit just one star in a multiple system, with the other stars appearing as bright points in the distance. The variety of lighting conditions on such worlds would create environments utterly unlike anything in our solar system, with shadows and seasons of bewildering complexity. In multi-star systems, the sky might never truly go dark. On planets orbiting in compact multiple star systems, the concept of night as we know it might not exist. When one sun sets, another might be rising or already high in the sky, bathing the world in continuous light from different directions. The darkness between stellar companions might be brief, lasting only hours before another sun illuminates the landscape from a different angle. Even when all suns are below the horizon, their combined light might scatter through the atmosphere, creating perpetual twilight rather than true darkness. Life on such worlds, if it exists, would have evolved without the daily cycle of light and dark that governs biological rhythms on Earth. The circadian clocks that regulate sleep, feeding, and reproduction in Earth organisms would find no natural anchor on worlds without true night. These perpetual day planets offer a glimpse into how different the relationship between life and light might be on other worlds. The lighting on these worlds would create strange double shadows. When two or more suns illuminate a landscape from different positions, objects cast multiple shadows that overlap and interact in complex ways. On a world with two suns of different colors, shadows might take on complementary hues: red where one sun's light is blocked, and blue where the other is occluded. The shadows would move at different rates, as each sun traces its own path across the sky, sometimes merging and sometimes separating throughout the day. During moments when the suns align, shadows would sharpen to single dark lines before splitting again as the suns diverge. The visual experience of walking through such a landscape would be disorienting to eyes evolved under a single sun. Artists and filmmakers have imagined these alien lighting conditions, but the reality on actual circumbinary worlds must be stranger than any simulation. Double shadows are a small detail that hints at how profoundly different everyday experience would be on a world lit by multiple stars. Some planets always show the same face to their star. Just as the Moon always shows the same face to Earth, some exoplanets are tidally locked to their stars, presenting one hemisphere in eternal day, while the other remains in endless night. This occurs when a planet orbits close enough to its star that gravitational forces slow its rotation until one side permanently faces the stellar furnace. Many planets orbiting red dwarf stars, the most common type of star in the galaxy, are thought to be tidally locked, because the habitable zone around these dim stars lies so close. The day side of such worlds receives constant bombardment by stellar radiation, while the night side radiates its heat into the cold vacuum of space. Tidal locking fundamentally changes what we consider habitable, as conditions on such worlds are unlike anything experienced on a rotating planet like Earth. Yet models suggest that atmospheric circulation could redistribute heat and create zones where life might survive. Tidally locked worlds represent perhaps the most common type of potentially habitable planet in the galaxy. On tidally locked worlds, one side burns while the other freezes. The temperature contrast between the day and night sides of a tidally locked planet can be extreme beyond imagination. The day side, facing perpetual noon, may reach temperatures that vaporize rock or melt metal, depending on the distance from the star. The night side, never seeing the star, could plunge hundreds of degrees below zero, cold enough to freeze gases like carbon dioxide or even nitrogen. Without an atmosphere to circulate heat, the contrast would be even more severe, creating worlds split between fire and ice. The atmosphere, if present, would flow constantly from the hot day side to the cold night side, creating planet-wide wind patterns unlike any on Earth. Where hot and cold air masses meet, violent storms might rage continuously along the boundary between day and night. The extreme dichotomy of tidally locked worlds creates environments that challenge our assumptions about what planets can be. A twilight zone between day and night might be the only habitable region. On tidally locked worlds, the transition zone where eternal day meets eternal night could host the most temperate conditions on the planet. This ring around the planet, sometimes called the terminator zone, would receive light at a perpetual low angle, like sunrise or sunset that never ends. Temperatures in this twilight realm would be moderated between the extremes of the day and night hemispheres, potentially falling into ranges that could support liquid water. Life, if it exists on such worlds, might be confined to this narrow band, evolving under the strange conditions of permanent dawn. The width of the habitable zone would depend on the thickness and circulation of the atmosphere, with thicker atmospheres spreading the temperate region wider. Some models suggest that life could spread beyond the terminator if atmospheric circulation effectively redistributes heat. The twilight zone is a uniquely alien environment, neither fully day nor fully night, but something entirely new. Some tidally locked planets have days longer than their years. The orbital mechanics of close orbiting planets can create strange relationships between days and years. A tidally locked planet does not rotate relative to its star, so from the perspective of someone on the day side, the sun never moves in the sky. The concept of a day becomes meaningless in the traditional sense, as the passage of time is not marked by sunrise and sunset. Yet the planet still orbits its star, completing a year in the time it takes to circle once around. For tidally locked planets orbiting red dwarfs, this orbital period might be just a few weeks, or even a few days by Earth standards. The seasons on such worlds, if they exist at all, would be driven by orbital eccentricity rather than axial tilt. Living on such a world would require abandoning most of our intuitions about how time is marked by celestial motion. The Terminator line could host perpetual sunsets that never end. Standing on the terminator of a tidally locked world, you would witness a sunset that never completes. The sun would hang at the horizon, its light streaming sideways across the landscape in permanent golden hour. The sky might be painted in the oranges and reds of perpetual twilight, with stars visible above the night-side hemisphere, even as daylight filled the other half of the sky. This endless sunset would create lighting conditions favored by photographers on Earth, but made permanent and universal on this alien world. The shadows would always be long, stretching toward the night side no matter what time it was. The psychological effect of never seeing the sun rise or set fully would profoundly shape any beings that evolved there, if consciousness is even possible in such environments. The Terminator is a place of eternal transition, frozen in the moment between day and night. On some worlds it rains molten glass, swept sideways by fierce winds. One of the most dramatic weather phenomena discovered on exoplanets occurs on HD 189733b, a hot Jupiter where temperatures exceed 1000 degrees Celsius and the atmosphere is filled with silicate vapor. As this vapor rises and cools, it condenses into tiny particles of silicate glass that fall as rain. But the rain does not fall straight down. Winds blowing at over 7,000 kilometers per hour sweep the glass sideways in horizontal sheets across the planet. The experience of standing on such a world, were it possible, would be like facing a sandblaster made of molten glass traveling at several times the speed of sound. The glass rain gives the planet its deep blue color, as the silicate particles scatter blue light preferentially, much like Earth's atmosphere but for entirely different reasons. This alien weather system was inferred from careful spectroscopic observations of the planet's atmosphere. Glass rain is just one example of how weather on other worlds can be more extreme and more strange than anything on Earth. Winds on certain exoplanets blow at thousands of miles per hour. The temperature differences between the day and night sides of tidally locked hot Jupiters drive atmospheric circulation at speeds that dwarf any wind on Earth. Jets of gas race around these planets at speeds exceeding 5,000 kilometers per hour, redistributing heat from the blazing day side to the frigid night side. These supersonic winds create pressure waves and shock fronts as the atmosphere attempts to equalize temperatures across the planet. The fastest winds measured on Earth, in hurricanes and tornadoes, reach speeds of a few hundred kilometers per hour. On hot Jupiters, such speeds would be considered gentle breezes. The energy driving these winds comes ultimately from the star, which pours radiation onto the day side continuously. Understanding these extreme wind patterns helps scientists model the heat distribution on tidally locked worlds and predict what conditions might exist on potentially habitable planets around red dwarfs. The winds of exoplanets push the boundaries of what atmospheric dynamics can achieve. Some planets have thick, hazy skies that obscure everything below. Attempts to study the atmospheres of some exoplanets have revealed a frustrating truth. Many are wrapped in hazes so thick that the deeper atmosphere remains hidden from view. These hazes form when stellar radiation breaks apart atmospheric molecules, creating reactive fragments that combine into complex organic compounds called tholins. On worlds like GJ1214b, the haze is so opaque that spectroscopic observations cannot penetrate to reveal the composition of the lower atmosphere. The orange haze of Saturn's moon Titan is a nearby example of similar chemistry, but on exoplanets the hazes can be even more extensive. These obscuring layers may be common on sub-Neptune worlds, hiding the transition between gaseous atmospheres and any solid or liquid surface below. The presence of haze complicates our ability to search for biosignatures, as the chemical fingerprints of life might be masked by the overlying murk. Hazy worlds remind us that not all exoplanets will give up their secrets easily. Metallic snow may fall on the hottest gas giants. On the blazing day sides of ultra-hot Jupiters, temperatures are high enough to vaporize metals like iron, magnesium, and even titanium. As powerful winds carry these metallic vapors toward the cooler night side, they condense and fall as metallic snow or rain. Iron snowflakes drifting down through alien clouds, titanium crystals forming in the upper atmosphere. The precipitation on these worlds is made of materials we associate with industry and construction. This metallic weather cycle continuously processes the heavy elements in the planet's atmosphere, with metals vaporizing on the hot side and precipitating on the cool side. The night side might have metallic puddles or even seas of liquid iron if temperatures allow, though the extreme conditions make such speculation difficult to confirm. Observations have detected the signatures of iron and other metals on the day sides of several ultra-hot Jupiters, supporting these models of metallic precipitation. Metal snow is among the most exotic forms of weather we have inferred on distant worlds. Clouds of vaporized rock drift through some alien atmospheres. At temperatures exceeding 2000 degrees Celsius, rock itself becomes a gas, rising through the atmosphere and condensing into clouds of mineral droplets or particles. These rock clouds have been detected on several ultra-hot exoplanets, their composition including silicates, oxides of iron and magnesium, and other refractory materials. The clouds form in layers, with different minerals condensing at different altitudes depending on their vaporization temperatures. From a distance, a planet with rock clouds might appear colored by the minerals present, perhaps reddish from iron oxides or gray from silicate dust. The weather cycle on such worlds involves the evaporation and condensation of materials we think of as solid and unchanging. Rain from rock clouds would not be gentle drops but searing drizzle of molten mineral that returns to the surface only to vaporize again. These extreme weather systems reveal how far the concept of clouds and rain can be stretched on other worlds. Dust storms on barren worlds might last for years without stopping. On rocky planets with thin atmospheres and abundant loose surface material, global dust storms could rage for extended periods far exceeding anything seen on Mars. The absence of oceans to moderate temperature extremes and the lack of vegetation to anchor soil would allow dust to be lifted continuously by thermal winds. Once airborne, fine particles could remain suspended for months or years, circling the planet and dimming whatever light reaches the surface. Such long-duration dust storms have been modeled for hypothetical desert super-Earths, where the combination of strong gravity and abundant dust creates persistent atmospheric opacity. The red deserts of these worlds would be scoured by winds carrying abrasive particles at high speeds, eroding any exposed rock over geological time. Life in such environments, if possible at all, would need to cope with perpetual twilight and the constant threat of being buried or sandblasted. Dust storm worlds represent the extreme end of arid planetary conditions. Some exoplanets complete their orbits in just a few hours. Among the fastest orbiting planets known are ultra-short period worlds that circle their stars in less than a day, with some completing a full orbit in just a few hours. These planets must orbit extremely close to their stars, skimming just above the stellar surface where gravitational forces and radiation are intense. The year on such a world, if we can even call it that, would flash by faster than an Earth day, with the planet experiencing continuous cycles of heating as it races around its star. The fastest known exoplanet, Kepler 70b, completes an orbit in just over 5 hours, traveling at speeds exceeding 700 kilometers per second. At such close distances, the planet is likely being slowly vaporized, its mass bleeding away into space as it spirals toward eventual destruction. Ultra-short period planets may represent worlds in their final stages of existence, caught in a death spiral toward their star. They demonstrate that planetary orbits can exist at the very edge of stability. Other planets take centuries to circle their stars. At the opposite extreme from the ultra-short period planets are worlds that orbit so far from their stars that a single year lasts longer than human civilizations have existed. The directly imaged planet HR 8799b, for example, takes over 400 years to complete one orbit, meaning it has moved only a tiny fraction of its path since it was first discovered. These distant giants receive so little starlight that they are barely warmer than the cosmic microwave background, glowing faintly with the residual heat of their formation. Observing a complete orbit of such planets is impossible within a human lifetime, so their orbital parameters must be calculated from the curvature of the tiny arc they trace over decades. Some planets may orbit even farther out, taking thousands or tens of thousands of years to circle their stars, invisible against the glare except when caught by the most sensitive instruments. These slow-orbiting worlds exist in a kind of cosmic stasis, barely changing their position from century to century. Some worlds orbit closer to their stars than Mercury does to our Sun. Mercury, the innermost planet in our solar system, orbits at an average distance of about 58 million kilometers from the Sun. Yet many exoplanets have been found orbiting far closer to their stars, some at distances of just a few million kilometers. At such proximity, the stellar surface would fill a significant portion of the sky, appearing as a blazing wall of fire rather than a distant disk. The radiation at these distances is thousands of times more intense than what Mercury receives, capable of melting rock and vaporizing metals. Planets surviving at such close distances must have masses and compositions that allow them to resist complete destruction. Some may be the iron cores of former gas giants, stripped of their atmospheres by the intense stellar radiation. Others might be rocky worlds that formed in place, though the physics of such formation is challenging to explain. Close-in planets push the boundaries of where worlds can exist. Distant planets drift so far from their stars, they barely receive any light. In the outer reaches of some planetary systems, worlds orbit at distances so great that their stars appear as little more than bright points in the sky. These distant planets receive so little stellar energy that they are effectively frozen, with surface temperatures approaching absolute zero. The light from their star, dim and cold, would be insufficient to warm ice or sustain photosynthesis. Yet these worlds are not entirely dark. Starlight, however faint, still arrives, and the glow of the galaxy itself provides a dim illumination. The distant planet 2MA SSJ 2126814OB orbits its star at a distance of about 1 trillion kilometers, so far that light takes about a month to travel between them. From such a planet, the star would be a bright point in a sky otherwise indistinguishable from that seen from interstellar space. These remote worlds exist at the very edge of what we consider a planetary system, barely bound by the faint gravitational tether of their distant sun. Some orbits are so elongated, the planets swing like cosmic comets. While most planets in our solar system travel on nearly circular paths, some exoplanets follow extremely elliptical orbits that carry them from scorching proximity to their star out to frigid distances. HD 80606b, one of the most eccentric planets known, approaches its star closely enough to be roasted by stellar radiation, before swinging out to distances comparable to Earth's orbit from the Sun. During close approach, the planet's temperature can rise by hundreds of degrees in just hours, creating violent weather as the atmosphere responds to the sudden heating. The origin of such extreme orbits likely involves gravitational interactions with other planets or stars that scattered the world onto its current path. These cometary orbits create seasonal variations far more extreme than anything on Earth, with brief periods of intense heat separated by long intervals of cold darkness. The planets are time capsules of past gravitational chaos, their eccentric paths recording ancient catastrophes in the orbital mechanics. Some planets float alone through space without any star at all. Not all planets orbit stars. Some drift through the galaxy entirely alone, unbound to any stellar system, wandering the void between the stars. These rogue planets, also called free-floating planetary mass objects, travel through interstellar space on journeys that may last billions of years. They receive no warming starlight, existing in perpetual darkness broken only by the faint glow of distant suns and the cosmic microwave background radiation left over from the Big Bang. Estimates suggest that rogue planets may be surprisingly common, with some studies proposing that there could be billions of them in the Milky Way alone, perhaps even outnumbering stars. Finding them is extraordinarily difficult because they emit no reflected starlight and only the faintest infrared glow from their own residual heat. Yet gravitational microlensing surveys have detected these dark wanderers, briefly brightening the light of background stars as they pass between us and more distant objects. Rogue planets represent a population of worlds unknown until recent decades, invisible orphans of the galaxy. Rogue planets were likely ejected from their home systems long ago. The origin of most rogue planets lies in the violence of early planetary system formation. When multiple planets form in a young system, gravitational interactions between them can send one or more worlds flying out into interstellar space. Close encounters between forming planets can exchange orbital energy, flinging the lighter or less tightly bound world onto an escape trajectory. Some rogue planets may have formed around stars that later exploded as supernovae, unbinding the planetary system entirely. Others might have been stripped from their host systems by the gravitational influence of passing stars in crowded stellar nurseries. A few may have formed directly from collapsing gas clouds, more like failed stars than traditional planets, though these objects blur the line between planet and brown dwarf. Whatever their origin, rogue planets carry with them a record of the gravitational chaos that expelled them, forever separated from the stellar family they once knew. These wandering worlds are dark, cold, and incredibly difficult to detect. The surface of a rogue planet would be among the coldest places in the universe, with temperatures potentially dropping to just a few degrees above absolute zero. Without the warmth of a nearby star, any atmosphere would freeze out onto the surface, forming layers of frozen nitrogen, carbon dioxide, or other volatile ices. The sky would be utterly dark, lit only by the faint glow of distant galaxies and the Milky Way stretching overhead. Detecting such worlds from Earth is exceptionally challenging, because they emit almost no light and reflect none. Infrared telescopes can occasionally spot the youngest and warmest rogue planets, still glowing faintly with the heat of their formation, but older rogues fade into near invisibility. Gravitational microlensing remains the most effective detection method, but it provides only a brief glimpse as the planet passes through our line of sight to a background star. The population of rogue planets remains largely uncounted and unexplored. Some rogue planets may still hold internal heat from their formation. Even without a star to warm them, rogue planets are not necessarily frozen to their cores. The heat generated during planetary formation, when colliding planetesimals release tremendous energy, can remain trapped within a planet's interior for billions of years. Larger rogue planets, with greater mass and thus more gravitational compression, would retain this primordial heat more effectively than smaller ones. The deep interiors of such worlds might remain molten, or at least warm, insulated by thick mantles of rock or ice that prevent the heat from escaping into space. This internal warmth could drive geological activity, perhaps even plate tectonics or volcanism, on worlds that appear frozen and dead from the outside. The contrast between a frigid surface and a warm interior creates possibilities for environments that might be more hospitable than the eternal darkness would suggest. Rogue planets remind us that warmth and energy can persist even in the coldest reaches of space. A few could harbor subsurface oceans warmed by radioactive decay. Perhaps the most intriguing possibility for rogue planets is that some might contain liquid water oceans beneath their frozen surfaces. The decay of radioactive elements like uranium, thorium, and potassium generates heat within planetary interiors, a process that continues for billions of years regardless of external conditions. If a rogue planet possessed a thick layer of ice overlying a rocky mantle rich in radioactive elements, the heat from decay could maintain liquid water at the boundary between rock and ice. Such subsurface oceans would be completely isolated from the surface cold, warmed from below rather than from above. These hidden seas would exist in perpetual darkness, but darkness is no barrier to life, as we have learned from Earth's own deep ocean ecosystems. Whether such life could actually arise and persist on a rogue planet remains unknown, but the mere possibility transforms these dark wanderers from barren rocks into potential oases in the cosmic desert. We have found planets with masses tens of times greater than Jupiter. Among the most massive planets discovered are super-Jupiters, gas giants with masses many times greater than our solar system's largest planet. Some of these colossal worlds contain enough material to form 10, 15, or even 20 Jupiters, yet they remain planets rather than stars, because they never gathered sufficient mass to ignite nuclear fusion in their cores. The sheer gravitational compression within these worlds creates pressures and temperatures unlike anything in our solar system, with exotic states of matter forming deep within their interiors. Metallic hydrogen, a bizarre material where hydrogen atoms share electrons in a conducting sea, likely forms vast layers within these super-Jupiters. Despite their immense mass, these planets may not be dramatically larger in diameter than Jupiter itself, since gravitational compression squeezes the additional material into a denser, more compact form. These giants challenge our understanding of how planets form, since gathering such enormous masses before the protoplanetary disk disperses requires exceptional conditions. They push the boundary of what we call a planet. Some giants blur the line between planet and failed star. At the upper mass limit of planets lie objects so massive that distinguishing them from brown dwarfs, the failed stars that never quite ignited fusion, becomes genuinely uncertain. The traditional boundary is often placed around 13 Jupiter masses, the point at which deuterium fusion can briefly occur, but this threshold is somewhat arbitrary. Some objects above this mass may have formed like planets through core accretion in a circumstellar disk, while some below it may have formed like stars through direct gravitational collapse. The method of formation, rather than mass alone, may ultimately determine whether an object is truly a planet or something else entirely. These boundary objects fascinate astronomers because they represent the transition zone between planetary and stellar formation, where the physics of both regimes overlap. Studying them helps us understand the full spectrum of objects that can form around stars. They remind us that the categories we create are human inventions, imposed on a continuous natural spectrum. Mini-Neptunes are among the most common types of exoplanets. One of the most surprising discoveries from exoplanet surveys is that planets between the size of Earth and Neptune, often called mini-Neptunes or sub-Neptunes, appear to be extraordinarily common in the galaxy. Our solar system has no planets in this size range, leaving a gap between rocky Earth and icy Neptune, yet this gap seems to be filled in many other systems. Mini-Neptunes typically have solid cores surrounded by thick envelopes of hydrogen and helium, giving them bloated appearances relative to their masses. They orbit at various distances from their stars, from close-in scorched worlds to more temperate zones where conditions might be milder. The abundance of mini-Neptunes suggests that planet formation naturally produces worlds of this type, making our solar system's lack of them an oddity requiring explanation. Some mini-Neptunes may gradually lose their atmospheres over time, transforming into smaller, denser super-Earths. These common worlds represent a planetary type we have yet to understand fully. Some puffy planets have atmospheres so inflated they could float. Among the strangest gas giants are the so-called puffy, or inflated planets, worlds with densities so low that they would float on water if an ocean large enough could be found. Some of these planets have the mass of Saturn but the volume of Jupiter, creating objects with the consistency of cotton candy. The cause of their inflation remains debated, but intense stellar heating, internal energy transport, and atmospheric chemistry all likely play roles. Close orbits around their stars pump energy into these planets, puffing up their atmospheres until they stretch to enormous diameters. The outer layers of puffy planets are so tenuous that determining where the planet ends and space begins becomes difficult. Their low densities make them ideal targets for atmospheric characterization, since the extended atmospheres block more starlight and provide stronger spectral signals. These inflated giants represent some of the most extreme planetary environments known. Giant planets can have spectacular ring systems larger than Saturn's. While Saturn's rings are iconic, they may be modest compared to the ring systems of some exoplanets. The young giant planet J1407b, for example, appears to possess a ring system over 200 times the diameter of Saturn's, stretching so far that it would be easily visible from Earth if it orbited our Sun. Such enormous rings might be composed of dust, ice, and rocky debris, the raw material from which moons could eventually coalesce. The transits of J1407b across its star created complex, irregular dimming patterns as different parts of the vast ring system blocked starlight. Gaps in the rings suggest the presence of forming moons, which clear orbital paths through the debris, much as Saturn's moons create gaps in its own rings. These colossal ring systems may be temporary features of young planetary systems, eventually condensing into moons and leaving behind only modest remnants. Witnessing such systems offers a glimpse into the processes that built our own solar system's moons. Super-Earths are rocky planets larger than Earth but smaller than Neptune. Super-Earths represent a class of planets with no analogue in our solar system, filling the size gap between our world and the ice giants. These rocky worlds typically range from about 1.5 to 10 Earth masses, large enough to retain substantial atmospheres yet small enough to remain primarily rocky, rather than gaseous. Their compositions likely include iron cores, silicate mantles, and potentially thick layers of water ice or liquid water. The surfaces of super-Earths might feature dramatic landscapes shaped by more intense geological activity than our planet experiences, with taller mountains, deeper valleys, and more powerful volcanic eruptions. The lack of super-Earths in our solar system makes them particularly intriguing, since they appear to be common around other stars. Understanding how these worlds form and evolve could reveal why our own planetary system developed differently. Super-Earths bridge the gap between familiar rocky worlds and the alien realm of gas and ice giants. Some super-Earths may be more habitable than our own world. The concept of superhabitability suggests that some super-Earths might actually provide better conditions for life than Earth itself. A planet slightly larger than ours could maintain plate tectonics more effectively, recycling carbon and regulating climate over longer periods. Stronger magnetic fields, generated by more vigorous internal dynamos, could better shield the surface from harmful stellar radiation. Shallower oceans spread across larger surface areas might create abundant coastal zones where life could flourish. The greater gravitational pull of a super-Earth would hold a thicker atmosphere, providing more robust climate buffering and better protection from impacts. Some scientists have speculated that life on a superhabitable world might have more time to evolve and diversify, potentially producing more complex ecosystems than Earth has known. While such ideas remain theoretical, they challenge our assumption that Earth represents the optimal world for life. The universe may contain planets better suited for biology than our own. These planets might have stronger gravity and thicker atmospheres. Standing on the surface of a super-Earth would feel quite different from being on our home planet. The stronger gravitational pull, perhaps 50% greater or more, would make every movement more effortful, and objects would feel heavier than their equivalent weight on Earth. This increased gravity would compress the atmosphere to higher densities, creating thicker, denser air that would affect everything from weather patterns to the flight of any aerial creatures that might exist. The higher surface pressure could dissolve more gases into oceans, potentially enriching the waters with nutrients or creating unusual chemical environments. Volcanic gases would accumulate more quickly in the atmosphere, and the cycling of elements between surface and interior would operate under different dynamics. Yet life, if it arose on such a world, would be adapted to these conditions from the beginning, experiencing them as normal rather than challenging. The diversity of gravitational environments across super-Earths represents one of the many ways alien worlds differ from our own. Some super-Earths lie in the habitable zone where liquid water could exist. The habitable zone around a star, sometimes called the Goldilocks zone, is the orbital region where temperatures allow liquid water to exist on a planet's surface. Numerous super-Earths have been discovered orbiting within their stars' habitable zones, making them prime candidates in the search for worlds that might support life. The super-Earth, LHS 1140b, for example, orbits within the habitable zone of its red dwarf star, receiving enough light to potentially warm its surface to temperate conditions. The habitable zone concept is a starting point rather than a guarantee, since actual surface temperatures depend heavily on atmospheric composition, cloud cover, and other factors. A super-Earth in the habitable zone might still be frozen if it lacks sufficient greenhouse gases, or roasting if its atmosphere traps too much heat. Nevertheless, these planets represent our best targets for finding environments where water flows, clouds form, and perhaps life emerges. Each new discovery in the habitable zone adds to the roster of potentially living worlds. A few may have Earth-like temperatures and moderate climates. Among the thousands of exoplanets discovered, a handful of super-Earths appear to have conditions that might produce Earth-like temperatures and stable, moderate climates. These worlds orbit at just the right distance from their stars, with masses suggesting rocky compositions capable of supporting liquid water oceans. The super-Earth Kepler 442b, orbiting a star cooler than our Sun, receives about 2/3 the light that Earth receives, potentially creating a slightly cooler but still temperate environment. TOI 700d, another promising candidate, orbits in the habitable zone of a red dwarf, and has attracted significant interest as a potentially habitable world. Whether these planets actually possess the atmospheres, water, and geological activity needed to create truly Earth-like conditions remains unknown, but the statistical likelihood that at least some do seems high. With billions of super-Earths in the galaxy, even a small percentage with temperate climates would mean millions of potentially habitable worlds. The search for Earth's cousins continues. Some planets orbit the collapsed remains of dead stars. Stars do not last forever, and when they die, they leave behind collapsed remnants such as white dwarfs, neutron stars, or black holes. Remarkably, planets have been found orbiting these stellar corpses, surviving the violent deaths of their parent stars, or forming anew from the debris. These worlds exist in environments utterly unlike any in our solar system, bathed in exotic radiation, or orbiting in the gravitational grip of objects denser than any ordinary matter. The discovery of planets around stellar remnants expanded our understanding of where worlds can exist, demonstrating that planetary systems can persist or reform even after stellar death. Some of these planets may be survivors from the star's main sequence life, transformed by the cataclysm but still intact. Others may have formed from material ejected during the star's death throes, second-generation worlds born from cosmic ashes. Planets around stellar remnants are witnesses to the end of stellar lives. Planets have been discovered circling white dwarfs. White dwarfs are the compact, cooling cores of dead stars like our Sun, and several have been found with planetary companions. The white dwarf WD 1856 plus 534, for example, has a Jupiter-sized planet orbiting remarkably close, a configuration that puzzled astronomers given the violence of the star's death. When a Sun-like star exhausts its fuel, it swells into a red giant that would engulf any close-in planets, so surviving worlds must have migrated inward after the star contracted to a white dwarf. Alternatively, some planets around white dwarfs may have formed from debris disks created when the dying star's gravity tore apart asteroids or smaller bodies. The environment around a white dwarf is strange, with the tiny stellar remnant glowing with residual heat, while gradually cooling over billions of years. Planets in such systems orbit compact objects no larger than Earth, yet containing the mass of the Sun. These systems offer glimpses of our own solar system's far future, when our Sun becomes a white dwarf. The first confirmed exoplanets were found orbiting a pulsar. Before the famous discoveries of planets around Sun-like stars, the first confirmed exoplanets were found in 1992 orbiting a pulsar. the rapidly spinning remnant of a supernova explosion. The pulsar PSRB 1257+12 has at least 3 planets, detected through tiny variations in the timing of its radio pulses caused by the gravitational pull of orbiting bodies. These planets orbit a neutron star so dense that a teaspoon of its material would weigh billions of tons, spinning dozens of times per second, and emitting beams of radiation that sweep through space like cosmic lighthouses. How these planets formed remains debated. They may be survivors from before the supernova, reconstituted from debris, or formed from material captured from a companion star. The radiation environment around a pulsar is extremely harsh, bombarding any nearby worlds with intense X-rays and particle streams. These pulsar planets are unlikely to be habitable, but their discovery marked the beginning of the exoplanet era and demonstrated that planets could exist in the most extreme environments imaginable. Some worlds may have survived the explosion of nearby supernovae. When massive stars die in supernova explosions, they release enough energy to outshine entire galaxies briefly, potentially destroying any planets orbiting too close. Yet some planets may survive these cataclysms, either because they orbit far enough to avoid complete destruction, or because they are dense enough to withstand the blast. A planet surviving a supernova would be transformed, its atmosphere stripped away, and its surface scorched by the intense radiation. The remnant of the star, whether neutron star or black hole, would continue to hold surviving planets in orbit, though their orbital parameters might be altered by the mass loss from the explosion. Some theoretical models suggest that particularly massive or distant planets could remain bound to the stellar remnant, circling the collapsed core for billions of years afterward. These survivor planets would be scarred witnesses to one of the most violent events in the universe. Finding and studying them could reveal how planetary systems respond to stellar catastrophes. Planets around stellar remnants are proof that worlds can endure cosmic death. The existence of planets around white dwarfs, neutron stars, and potentially even black holes demonstrates that planetary systems are remarkably resilient. Worlds can survive transformations that would seem to guarantee destruction, adapting to the new conditions left behind by dying stars. This resilience suggests that planets, once formed, are difficult to destroy entirely, persisting through the most extreme transitions a stellar system can experience. The reformed systems around stellar remnants may even represent opportunities for new planetary formation, as debris disks and captured material coalesce into new worlds. These survivor planets carry information about the conditions before and during stellar death, serving as cosmic fossils of their parent stars' final moments. Studying them illuminates not just the fate of individual systems, but the long-term evolution of planetary populations across the galaxy. They remind us that endings can also be beginnings in the cosmic cycle of creation and destruction. We have detected planets around stars just a few million years old. The youngest planetary systems offer windows into the birth of worlds, showing us processes that occurred in our own solar system over 4 billion years ago. Protoplanetary disks, the swirling rings of gas and dust around newborn stars, have been imaged in remarkable detail, revealing gaps and structures carved by forming planets. Some of these young stars, mere millions of years old compared to our Sun's billions, already host detectable planets, demonstrating that world building begins almost immediately after star formation. The planet PDS-70b, for example, orbits within a gap in its star's protoplanetary disk, still gathering material as it grows. These infant planets are hot, glowing with the energy of their formation, and can be directly imaged against the cool backdrop of their parent disks. Studying them allows astronomers to test theories of planet formation in real time. watching processes that otherwise can only be inferred from the finished products. Young planetary systems are laboratories for understanding cosmic construction. Some planets are still actively gaining mass from surrounding disks. Planet formation is not instantaneous but extends over millions of years as growing worlds sweep up gas and dust from their surroundings. Some exoplanets have been caught in the act of accretion, actively drawing material from their parent disks and adding to their own mass. The material flows onto the planet through spiraling streams, heating up as it falls and creating luminous accretion signatures that can be detected from Earth. These actively accreting planets provide direct evidence of how gas giants build their massive atmospheres, confirming theoretical models developed decades before such observations were possible. The rate of accretion varies depending on the local disk conditions, with some planets growing rapidly while others develop more slowly. Eventually, the disk material is depleted or dispersed, and the planet's growth phase ends, leaving it to evolve in isolation. Witnessing active accretion connects us to the dynamic processes that shaped our own solar system. Certain worlds may have formed from the remains of destroyed planets. Not all planets survive unchanged from their formation. Some worlds are destroyed by collisions, stellar encounters, or tidal forces, their remnants available for recycling into new objects. Second-generation planets might form from debris disks created when earlier worlds were shattered, inheriting material that had already been processed through a previous planetary cycle. The debris around some white dwarfs, for instance, likely originated from asteroids or small planets torn apart by the dead star's gravity, and this material could potentially recondense into new bodies over time. In other cases, massive collisions between planets might generate enough debris to form smaller worlds, or large moons from the fragments. The Earth's moon is thought to have formed from such a collision, making it in some sense a second-generation object. These recycled worlds would carry chemical signatures of their destruction, incorporating elements processed by the previous generation of planets. Planetary systems are not static, but continuously evolving. Some exoplanets may have once been part of another star system entirely. Gravitational encounters between passing stars can sometimes exchange planets, transferring a world from one stellar family to another. In the crowded stellar nurseries where most stars form, such encounters may have been relatively common, meaning some planets could orbit stars very different from those around which they formed. An exchanged planet would carry isotopic and chemical signatures reflecting its birth environment, potentially revealing its foreign origin to careful observers. The process works both ways. Stars can lose planets to passing neighbors, while also potentially capturing wanderers. Our own solar system may contain such immigrants, though identifying them definitively would be challenging. The concept of exchanged planets expands the notion of planetary families, suggesting that the worlds orbiting a given star need not share a common origin. Stars are not isolated islands, but members of a galactic community, where matter and worlds occasionally migrate between systems. We have witnessed hints of planetary destruction in real time. Some observations suggest we are witnessing planetary systems in the process of destruction, with worlds being torn apart, consumed, or otherwise demolished. The star WD 1145+017, for example, shows irregular dips in brightness caused by clouds of debris orbiting the white dwarf, likely the remnants of one or more planetesimals being gradually shredded by tidal forces. Other stars show signatures of rocky material polluting their atmospheres, indicating that asteroids or planetary fragments have recently fallen into the stellar surface. A few dramatic cases involve planets on death spirals, gradually migrating inward toward eventual destruction in their stars' outer layers. These glimpses of planetary death remind us that not all worlds survive indefinitely. Some meet violent ends through interactions with their stars or other planets. Witnessing destruction in progress provides unique data about planetary compositions and orbital dynamics. It also places our own solar system's relative stability in perspective. Some exoplanets are bombarded by intense stellar flares. The stars hosting exoplanets are not all calm and steady like our Sun, but include many that erupt with powerful flares capable of dramatically affecting their planetary companions. Flaring stars, particularly young stars and active red dwarfs, can release bursts of energy millions of times more powerful than typical solar flares, flooding nearby planets with intense ultraviolet and X-ray radiation. A planet caught in such a stellar tantrum would experience surges of damaging radiation that could strip away atmospheric gases, destroy organic molecules, and sterilize exposed surfaces. The red dwarf Proxima Centauri, host to the nearest exoplanet to Earth, is known to flare frequently, raising questions about whether its planet could retain an atmosphere or support life. Flares are unpredictable, creating environments where conditions can change dramatically within hours. Planets orbiting flaring stars must develop some form of protection, whether thick atmospheres, strong magnetic fields, or deep oceans, to shield any potential biosphere. Stellar activity is a crucial factor in evaluating planetary habitability. Planets near active stars risk having their atmospheres stripped away. Over time, the cumulative effect of stellar radiation can erode planetary atmospheres entirely, leaving behind bare, airless worlds. This atmospheric stripping occurs when high-energy photons and stellar wind particles knock gas molecules to escape velocity, allowing them to leak into space. Planets lacking strong magnetic fields are particularly vulnerable, since magnetic shielding can deflect much of the damaging particle radiation. Mars serves as an example in our own solar system, having lost most of its atmosphere over billions of years after its internal dynamo died and its magnetic field faded. Exoplanets orbiting closer to their stars experience even more intense radiation and correspondingly faster atmospheric loss. Some hot Jupiters are observed to be actively losing their atmospheres, trailing tails of evaporating gas like cosmic comets. The battle between atmospheric replenishment through volcanism and outgassing versus loss through stellar stripping determines whether a planet can maintain its gaseous envelope. Many potentially habitable planets may have become barren through this relentless erosion. Other worlds bask in the calm glow of quiet, stable red dwarfs. Not all red dwarfs are violent and flaring. Some are remarkably quiet and stable, providing consistent illumination to their planetary companions over billions of years. Planets orbiting these calmer stars may enjoy more benign radiation environments, with less risk of atmospheric stripping and fewer sterilizing events. The stability of such stars makes them attractive targets in the search for habitable worlds, since life would have long, uninterrupted periods to develop without catastrophic disruptions. Some red dwarfs are so stable that they will continue shining for trillions of years, potentially providing habitable conditions long after stars like our Sun have died. The TRAPPIST-1 system, with its 7 rocky planets, orbits a relatively quiet red dwarf that may offer stable conditions for habitability. Identifying which red dwarfs are calm and which are active is a key priority for exoplanet researchers. The temperament of a star may matter as much as its luminosity for determining whether its planets can support life. Some planets might be wrapped in auroras that never end. On Earth, auroras occur when charged particles from the Sun interact with our magnetic field and atmosphere, creating shimmering curtains of light near the poles. On some exoplanets, similar processes might create auroras of unprecedented scale and permanence, potentially visible across entire hemispheres. Planets orbiting close to their stars or exposed to intense stellar winds would receive far more charged particles than Earth, potentially driving continuous auroral displays that never fade. The hot Jupiter HD 189733b is estimated to have auroras 1,000 times more powerful than any on Earth, powered by the intense radiation from its nearby star. These alien light shows would involve different colors depending on atmospheric composition, with hydrogen producing red and ultraviolet emissions rather than Earth's characteristic green and red. A night sky wrapped in permanent auroral glow would be breathtakingly beautiful, though the radiation responsible might be harmful to any life attempting to survive. These perpetual auroras are reminders of the dynamic interactions between planets and their stars. Habitability depends not just on distance, but on stellar temperament. When evaluating whether a planet might support life, astronomers consider not just its distance from its star, but the star's overall behavior and history. A planet in the habitable zone of an active flaring star might be less hospitable than one somewhat outside the habitable zone of a calmer star. The age of the star matters too, since young stars tend to be more active than older, settled ones. The type of radiation a star emits affects atmospheric chemistry and the potential for life, with different stellar types favoring different chemical pathways. A star's magnetic activity, rotation rate, and mass all influence the radiation environment experienced by its planets. Even stars that are currently calm may have been more active in their youth, potentially stripping atmospheres from planets before they could develop protective mechanisms. The full history of stellar activity shapes planetary evolution in ways we are only beginning to understand. Habitability is a complex equation with stellar temperament as a key variable. Some planets orbit their stars in the opposite direction of stellar rotation. In our solar system, all major planets orbit in the same direction that the Sun rotates, a consequence of the orderly formation from a spinning disk of gas and dust. Yet some exoplanets have been found orbiting in the opposite direction, moving retrograde against the spin of their host stars. This backward motion cannot arise from simple disk formation, and requires some dramatic event to have flipped the planet's orbit. The hot Jupiter WASP-17b was among the first retrograde planets discovered, its backward orbit challenging assumptions about how planetary systems evolve. Various mechanisms can produce retrograde orbits, including gravitational interactions with other planets, the influence of distant stellar companions, or close encounters with passing stars. Once a planet is in a retrograde orbit, it remains stable, continuing to circle backward indefinitely. These contrary worlds demonstrate that planetary systems can be violently rearranged long after their initial formation. They are evidence of hidden chaos in systems that might otherwise appear orderly. Backward orbits likely formed through chaos or gravitational encounters. The origin of retrograde orbits lies in the complex gravitational dynamics that can affect planetary systems over their lifetimes. One mechanism involves the Kozai-Lidov effect, where a distant companion, whether planet or star, gradually tilts and deforms a planet's orbit until it flips entirely. This process can take millions of years, slowly pumping the orbit to higher and higher inclinations until retrograde motion results. Alternatively, close encounters between planets in unstable systems can scatter one world onto a backward-moving trajectory. Planet-planet scattering is thought to be common in young systems with multiple giant planets, with the survivors often left on eccentric or inclined orbits. Some retrograde hot Jupiters may have migrated inward after being scattered, their high inclinations gradually damping as tidal forces circularize their orbits. The variety of mechanisms capable of producing retrograde motion suggests that many apparent oddities in planetary systems can be explained by dynamical chaos. The universe is full of hidden violence recorded in planetary orbits. Some exoplanets have extremely tilted orbits compared to their star's equator. Beyond simply orbiting backward, some planets travel on paths severely tilted relative to their stars, equatorial planes. These highly inclined orbits carry planets above and below the stellar equator, creating geometries quite unlike the flat disk of our solar system. An extremely tilted planet would experience strange seasons, with its host star appearing to climb high in the sky during some parts of the orbit and remaining near the horizon during others. The hot Jupiter HAT P7b orbits its star at an inclination of about 80 degrees, nearly perpendicular to the stellar equator. Such high inclinations, like retrograde orbits, require some form of gravitational perturbation to achieve, since planets forming from flat disks should remain in the disk plane. Systems with highly tilted planets often contain other massive bodies whose gravitational influence could have caused the misalignment. These tilted worlds reveal that the apparent order of our solar system is not universal. Certain planets spin backwards compared to their orbital direction. Separate from orbital direction, planets themselves have spin, and some exoplanets may rotate in directions opposite to their orbital motion. On Earth, our spin and orbital motion are broadly aligned, with both moving in the same eastward direction, but Venus spins backward relative to its orbit around the Sun. Some exoplanets may exhibit similar retrograde rotation, perhaps due to ancient collisions that knocked them onto their current spin axes. Measuring the spin direction of exoplanets is extremely challenging with current technology, but the discovery of unusual axial tilts in our own solar system suggests that spin-orbit misalignment is possible. A planet spinning backward would experience sunrises in the west and sunsets in the east, a complete reversal of what we know on Earth. The forces that can reverse a planet's spin include giant impacts, tidal locking, and chaotic dynamics during formation. These spinning anomalies remind us that orientation is not fixed, but shaped by history. These unusual motions hint at dramatic, violent pasts. Every planet with a strange orbit or unusual spin carries the scars of events long past, written in its motion for those who can read them. Retrograde orbits, extreme tilts, and backward spins are all signatures of gravitational encounters, collisions, or interactions that dramatically altered a world's trajectory. Reconstructing these histories requires understanding the full dynamics of the planetary system, including any companions, past or present, that might have influenced the planet's motion. Some systems may have lost planets entirely, ejected during the same events that scattered survivors onto unusual orbits. The survivors that remain are fossil records of ancient chaos, their orbits preserving information about conditions billions of years ago. By studying these unusual motions, astronomers piece together the violent histories of planetary systems that might otherwise appear calm. The cosmos is full of worlds marked by drama we can only infer from the evidence they carry. Some planets are locked in precise gravitational dances with their neighbors. Orbital resonance occurs when planets influence each other through regular gravitational tugs that repeat at precise intervals, creating stable, synchronized relationships. When two planets are in resonance, their orbital periods form simple ratios, such as 2:1 or 3:2, meaning that their alignments repeat in regular patterns. Each time the planets pass closest to each other, they exchange a small gravitational kick that reinforces their orbital configuration, rather than disrupting it. In our own solar system, Pluto and Neptune are in a 3:2 resonance, with Pluto completing 2 orbits for every 3 of Neptune, preventing close encounters despite their crossing paths. Exoplanetary systems frequently exhibit similar resonances, sometimes involving multiple planets in intricate chains of synchronized motion. These gravitational dances are not accidental, but arise naturally from the physics of planet formation and migration. Resonant systems represent a kind of orbital music, with each planet playing its part in a cosmic symphony. Orbital resonances create stable, repeating patterns that last billions of years. The stability provided by orbital resonance can allow planetary configurations to persist essentially unchanged for the entire lifetime of their star. When planets are locked in resonance, their mutual gravitational interactions actually protect them from perturbations that might otherwise destabilize their orbits. The regular gravitational kicks they exchange keep them synchronized, preventing the slow accumulation of changes that could lead to orbital chaos. The 4 Galilean moons of Jupiter, Io, Europa and Ganymede are locked in a famous 4:2:1 resonance that has persisted for billions of years. Similar long-lasting resonances likely exist in exoplanetary systems, preserving orbital architectures from the early days of system formation. This stability has implications for habitability, since a planet in a stable resonance is protected from the orbital instabilities that could cause climate catastrophes. Resonance systems are islands of order in a universe where gravitational chaos constantly threatens. Some systems have long chains of resonance involving many planets. The most spectacular resonance systems involve not just pairs of planets, but entire chains, where each successive planet is resonant with its neighbors. The TRAPPIST-1 system provides a remarkable example, with 7 Earth-sized planets, all participating in a linked resonance chain. Each adjacent pair has orbital periods related by simple ratios, and the whole system moves like an intricate clockwork mechanism. These resonance chains likely form during planetary migration, when planets moving through the protoplanetary disk encounter each other and lock into resonant configurations. Maintaining a long chain of resonance requires delicate conditions, as any significant perturbation could break the chain and send planets scattering. The existence of such chains suggests that migration and resonance capture were common processes in planet formation, even if many chains have since been broken. Systems preserving these chains are windows into the gentle, orderly phase of planetary system assembly. These arrangements are delicate, but beautifully harmonious. There is a genuine mathematical beauty to resonant planetary systems, with their simple orbital ratios and repeating patterns. Astronomers sometimes describe resonant systems using musical terminology, noting that the ratio between orbital periods corresponds to musical intervals. A 2:1 resonance is analogous to an octave, while a 3:2 resonance corresponds to a perfect fifth. The TRAPPIST-1 system has been translated into actual music, with each planet's orbit assigned a note that plays when the planet completes an orbit, creating surprisingly harmonious melodies. This harmony reflects the underlying physics, where resonance represents a kind of energetic minimum, a configuration toward which systems naturally evolve. Yet the beauty is fragile. The same conditions that create resonance can also lead to instability if the balance is disturbed. These planetary harmonies remind us that the universe, for all its chaos, contains pockets of profound order. Other systems appear unstable and may collapse in the future. Not all planetary systems are stable, and some configurations observed today may not persist indefinitely. Systems with planets on crossing orbits, near resonances that just miss being protective, or multiple massive planets in close proximity may be inherently unstable. Computer simulations of such systems often show eventual collisions, ejections, or dramatic orbital rearrangements over millions or billions of years. The system Kepler-36, for example, has 2 planets with extraordinarily close orbits that come within less than 2 million kilometers of each other, a configuration that seems precarious, though it has evidently survived for millions of years. Our own solar system, despite its apparent stability, has a small probability of orbital instability in the very distant future, with Mercury's orbit potentially becoming chaotic. Unstable systems that exist today are survivors so far, but their long-term fates remain uncertain. They represent snapshots of dynamical experiments still in progress. Exomoons remain elusive, but hints of their existence have been detected. Despite detecting thousands of exoplanets, astronomers have not yet confirmed the existence of a single exomoon orbiting any of them. The challenge is one of sensitivity and precision. Moons are smaller than their parent planets and produce even tinier signals that are easily lost in observational noise. Yet, tantalizing hints have emerged that suggest exomoons may exist around some of the planets we have found. The candidate exomoon Kepler 1625b, if confirmed, would be a Neptune-sized moon orbiting a Jupiter-like planet far larger than any moon in our solar system. Detecting such a moon required analyzing subtle variations in the transit timing of its parent planet, looking for the gravitational effects a large moon would produce. Other candidates have been proposed but remain unconfirmed, hovering at the edge of detectability. The first definitive exomoon detection will open an entirely new field of study, revealing whether moons are as common around exoplanets as they are in our solar system. Until then, the existence of exomoons remains a tantalizing likelihood rather than a confirmed fact. Some giant exoplanets might have entire moon systems of their own. In our solar system, the giant planets Jupiter and Saturn each host dozens of moons, some larger than Mercury, and potentially hosting subsurface oceans. There is every reason to expect that giant exoplanets would similarly possess extensive moon systems, with populations of satellites ranging from tiny captured asteroids to world-sized bodies. These moons would form from the same circumplanetary disks that surrounded their parent planets during formation, or be captured later from passing debris. A Jupiter-like exoplanet in the habitable zone of its star might have moons with conditions suitable for life, orbiting not the star directly, but a massive intermediate body. The gravitational dynamics of such systems would be complex, with moons influencing each other's orbits and potentially migrating inward or outward over time. Some moons might be tidally locked to their planets, experiencing the same extreme heating as close-in planets experience from their stars. The potential diversity of exomoon systems suggests that the satellites of giant planets may be as interesting as the planets themselves. Exomoons could have subsurface oceans like Europa or Enceladus. The moons of our solar system's giant planets include several with global subsurface oceans, heated by tidal forces rather than direct sunlight. Europa, orbiting Jupiter, almost certainly possesses a liquid water ocean beneath its icy shell, maintained by the flexing of its interior as Jupiter's gravity stretches and squeezes it. Enceladus, orbiting Saturn, actively vents water vapor and ice particles from its subsurface ocean through cracks in its icy surface. Exomoons around giant planets could experience similar tidal heating, potentially maintaining liquid water even in regions far too cold for sunlight alone to prevent freezing. A large moon orbiting a massive exoplanet in the outer reaches of a planetary system might be more habitable than any planet in that system's traditional habitable zone. The energy source would be gravitational rather than stellar, independent of distance from the central star. These tidally heated exomoons represent an entirely different pathway to habitability, one that could vastly expand the number of potentially living worlds. Some planets may have ring systems hundreds of times larger than Saturn's. The ring system of Saturn is one of the most iconic features in our solar system, but it may be modest compared to rings around some exoplanets. The young planet J1407b appears to possess a ring system over 200 times the diameter of Saturn's, so vast that if it replaced Saturn's rings, they would be easily visible from Earth with the naked eye. This enormous ring system was detected through the complex dimming pattern it produced as the planet transited its star, with multiple distinct rings casting shadows of varying depth. Gaps in the rings suggest the presence of forming moons, clearing orbital paths through the debris much as shepherd moons maintain gaps in Saturn's rings. Such extensive rings may be temporary features of young planetary systems, eventually coalescing into moons, or dispersing over millions of years. Observing them provides snapshots of moon formation in progress, processes that shaped our own solar system billions of years ago. Exoplanet ring systems offer spectacular laboratories for understanding satellite formation. Rings cast deep shadows that help us detect distant planetary systems. The very features that make ring systems spectacular also make them useful for detection, as rings can cast significant shadows across their parent stars during transits. A planet with an extensive ring system will produce a transit light curve with characteristic features, including a gradual dimming as the outer rings begin to block starlight and complex variations, as gaps and density changes in the rings cross the stellar disk. Analyzing these light curves allows astronomers to infer the structure of ring systems too distant to image directly. The transit method has proven sensitive enough to detect not just planets but the additional signatures rings produce, opening a window into planetary features beyond simple radius and orbital period. Rings also indicate conditions in the planetary environment, such as the presence of shepherd moons, recent impacts, or ongoing debris generation. These shadows cast across distant stars carry rich information about planetary systems we may never see up close. They remind us that even the most subtle signals can reveal remarkable cosmic structures. We detect many exoplanets by the shadows they cast during transits. The transit method has proven to be the most prolific technique for discovering exoplanets, responsible for the vast majority of confirmed worlds. When a planet passes between its star and Earth, it blocks a tiny fraction of the starlight, creating a measurable dip in brightness that repeats with each orbit. The depth of this dip reveals the planet's size relative to its star, while the duration indicates the orbital speed and distance. By monitoring thousands of stars simultaneously, space telescopes like Kepler have detected the subtle dimming caused by planets ranging from gas giants to worlds smaller than Earth. The transit method works best for planets with orbits aligned to our line of sight, meaning many planets are missed simply because their orbits are tilted away from us. Nevertheless, the planets detected through transits have transformed our understanding of planetary systems, revealing the diversity and abundance of worlds throughout the galaxy. Every transit is a shadow play performed on a cosmic stage. The wobble a planet induces in its star reveals its presence. Before the transit method dominated exoplanet discovery, the radial velocity technique, also known as the Doppler wobble method, was the primary means of finding new worlds. As a planet orbits its star, its gravitational pull causes the star to move in a small circle or ellipse, shifting the star's light slightly toward the blue when approaching and toward the red when receding. By precisely measuring these spectral shifts, astronomers can detect the presence of an orbiting planet and determine its minimum mass and orbital period. The radial velocity method is most sensitive to massive planets on close-in orbits, since these produce the largest stellar wobbles, but improvements in instrument precision have enabled detection of increasingly smaller worlds. Combining radial velocity measurements with transit observations allows astronomers to determine both the mass and radius of a planet, yielding its density and clues to its composition. The wobble of distant stars carries encoded information about their planetary companions. Direct imaging has captured the faint glow of a few distant worlds. While most exoplanets are detected indirectly, through their effects on starlight or stellar motion, a small number have been directly photographed. Direct imaging is extraordinarily challenging because planets are millions to billions of times fainter than their host stars and separated by tiny angular distances on the sky. Sophisticated techniques, including coronagraphs that block starlight and adaptive optics that correct for atmospheric distortion, have enabled astronomers to image a handful of young, massive and distant planets. The planets of the HR 8799 system were among the first to be directly imaged, appearing as faint dots orbiting their star in successive observations. Young planets are easier to image because they still glow brightly with the heat of their formation, radiating enough infrared light to be detected. Direct imaging provides unique information about planetary atmospheres and orbits that other methods cannot easily access. The images, though blurry by everyday standards, represent remarkable technical achievements. Space telescopes like Kepler and TESS have discovered thousands of planets. The Kepler Space Telescope, launched in 2009, revolutionized exoplanet science by staring at a single patch of sky for years, monitoring over 100,000 stars for the telltale dimming of planetary transits. During its primary mission, Kepler discovered over 2,000 confirmed planets and identified thousands more candidates awaiting confirmation. The mission revealed that planets are common throughout the galaxy, with most stars hosting at least one world and many hosting complex multi-planet systems. Following Kepler, the Transiting Exoplanet Survey Satellite, or TESS, has expanded the search to cover nearly the entire sky, focusing on brighter, closer stars, whose planets will be easier to characterize with follow-up observations. TESS has already discovered hundreds of planets and continues to add to the count. These space-based observatories have transformed exoplanet detection from a rare occurrence to a routine discovery, building catalogs of worlds that will keep astronomers busy for decades. They represent humanity's first comprehensive census of planets beyond our solar system. We are learning to study the chemistry of alien atmospheres from starlight. When a planet transits its star, some starlight passes through the planet's atmosphere, picking up spectral signatures of the gases present. By comparing the spectrum of the star during transit to its spectrum outside transit, astronomers can identify molecules in the planetary atmosphere. This technique, called transmission spectroscopy, has detected water vapor, carbon dioxide, methane, and other compounds in the atmospheres of hot Jupiters and smaller worlds. The James Webb Space Telescope has dramatically advanced this field, providing unprecedented sensitivity to the faint spectral fingerprints of atmospheric gases. Detecting biosignature gases, molecules that might indicate the presence of life, is a major goal of atmospheric characterization. While no definitive biosignatures have yet been found, the tools to search for them are now in hand. Each atmospheric detection adds to our understanding of planetary chemistry and the conditions on worlds we will never visit directly. Starlight carries coded messages about the air of alien worlds. Some planets exist in cosmic Goldilocks zones, where temperatures are just right. The concept of a habitable zone, sometimes called the Goldilocks zone, refers to the orbital region around a star where temperatures allow liquid water to exist on a planet's surface. Not too hot and not too cold, These zones represent the sweet spot where the conditions for life as we know it are most likely to be met. The location and width of a habitable zone depend on the star's luminosity, with bright hot stars having zones farther out and dim cool stars having zones closer in. For a Sun-like star, the habitable zone stretches roughly from the orbit of Venus to just beyond Mars, though the exact boundaries depend on atmospheric assumptions. Planets discovered within these zones are considered prime candidates for potentially harboring life, attracting intense scientific interest and follow-up observations. The habitable zone concept is a starting point rather than a guarantee, since atmospheric composition, geological activity, and other factors all influence whether a planet is truly hospitable. Nevertheless, finding worlds in these cosmic sweet spots is a major goal of exoplanet science. The habitable zone is a narrow ring where liquid water could exist. Liquid water is considered essential for life as we know it, serving as the solvent in which biochemistry occurs, and the medium through which nutrients and waste products are transported. The habitable zone is defined by the range of distances where stellar heating could maintain liquid water on a planetary surface, assuming appropriate atmospheric pressure and composition. Too close to the star, water would vaporize. Too far, it would freeze. This definition is deliberately conservative, focusing on surface conditions similar to Earth's, though life might exist in more exotic environments as well. The width of the habitable zone varies from star to star, and for red dwarf stars, it can be quite narrow, requiring planets to orbit very close to their hosts. Over a star's lifetime, the habitable zone shifts outward as the star brightens with age, meaning that planets currently in the zone might not have been habitable in the past, or might not remain so in the future. The habitable zone is a dynamic concept that changes with stellar evolution. Life on exoplanets might look nothing like life on Earth. If life exists on other worlds, it may have taken forms utterly unlike anything in Earth's biosphere. The chemistry of alien life might be based on different elements or molecules, perhaps using silicon instead of carbon or ammonia instead of water. The energy sources driving metabolism could include unfamiliar reactions, tapping into geothermal heat, radioactive decay, or exotic chemistry rather than sunlight. Physical forms would be shaped by the local environment, with life in high-gravity worlds perhaps being flat and sprawling, while life in dense atmospheres might float or fly. Even the basic units of inheritance and variation might differ from DNA and proteins, using informational molecules we have not imagined. The diversity of life on Earth, from bacteria to blue whales, hints at the range of possibilities but probably represents only a tiny fraction of what biology could achieve. Alien life might be so different that recognizing it as life would require careful analysis. We should expect the unexpected. We have just started to search for biosignatures on distant worlds. The search for biosignatures, chemical or physical signs of life, in exoplanet atmospheres, has become a major focus of modern astronomy. Gases like oxygen, methane, and ozone could indicate biological activity, though each can also be produced by non-biological processes. The challenge lies in detecting these gases in the thin, faint atmospheres of distant planets, and in interpreting their presence correctly. The James Webb Space Telescope has begun examining the atmospheres of potentially habitable worlds, searching for the spectral fingerprints of biosignature gases. Future missions, including proposed space telescopes designed specifically for this purpose, will extend the search to more and smaller planets. Finding definitive evidence of life beyond Earth would be one of the most profound discoveries in human history, forever changing our understanding of our place in the universe. While no biosignatures have been confirmed yet, the tools and techniques to search for them are now in hand. The search has begun in earnest. Some worlds could be home to life in environments we would find deadly. Extremophiles on Earth thrive in conditions once thought incompatible with life. From boiling hot springs to frozen Antarctic ice, from highly acidic lakes to the crushing pressure of deep ocean trenches. These organisms demonstrate that life can adapt to a remarkable range of environments, suggesting that exoplanets we might dismiss as uninhabitable could actually support exotic biospheres. A world bathed in intense radiation might host life in subsurface refuges, while a planet with a toxic atmosphere might have organisms that metabolize the very chemicals that would kill us. Tidal heating could maintain liquid water oceans on frozen moons, while thick hydrogen atmospheres could keep rocky worlds warm far from any star. The boundaries of habitability continue to expand as we learn more about the resilience and adaptability of life. We should be cautious about dismissing any world as lifeless, without thorough investigation. The universe may be teeming with life in places we least expect. Some worlds lie in the quietest corners of the galaxy. The Milky Way is not a uniform environment. Some regions are crowded with stars, bathed in radiation, and prone to gravitational disturbances, while others are relatively calm and isolated. Planets in the quieter regions of the galaxy may enjoy greater stability over cosmic timescales, with less risk of nearby supernovae, gamma-ray bursts, or gravitational perturbations from passing stars. Our own solar system occupies a relatively benign location, far from the chaotic central bulge and the active star-forming regions of the spiral arms. Planets in similar galactic suburbs might have long, uninterrupted periods during which life could develop and evolve. The concept of a galactic habitable zone considers not just the distance from a planet's star, but also the location within the broader galaxy. Some researchers suggest that the best places for life are neither too close to the galactic center, where radiation is intense, nor too far out, where heavy elements needed for rocky planets are scarce. Galactic geography matters for planetary habitability. Others speed through chaotic, crowded starfields. In contrast to the quiet galactic suburbs, some planetary systems exist in the dense, dynamic environments of the galactic center, globular clusters, or young star-forming regions. These crowded environments subject planets to frequent gravitational encounters with passing stars, higher radiation levels from nearby supernovae and active galactic nuclei, and the general turbulence of stellar nurseries. Planets in such regions may be at greater risk of orbital disruption, atmospheric stripping, or sterilizing radiation events. Yet the same environments that pose challenges for habitability also create opportunities for planet formation, with abundant gas and dust available to build new worlds. Some planets may be born in crowded regions, only to be ejected into quieter space as their systems evolve. The interplay between planetary formation and galactic environment shapes the diversity of worlds throughout the Milky Way. Crowded starfields are both cradles and crucibles for planets. Planets have been discovered in ancient star systems older than Earth. The oldest planetary systems formed billions of years before our own solar system coalesced from its primordial nebula, and some of these ancient worlds have been detected orbiting their aged stars. These planets have witnessed cosmic eras we can only imagine, existing through epochs when the galaxy was younger and the universe itself was still settling into its present form. The oldest known planetary system, Kepler 444, contains 5 rocky planets orbiting a star that is over 11 billion years old, formed when the universe was less than 3 billion years after the Big Bang. These ancient worlds have had vastly more time for any life that might have arisen to develop and evolve, potentially reaching levels of complexity far beyond anything on Earth. The discovery of such old planets demonstrates that planet formation began early in cosmic history and has continued throughout the universe's evolution. ancient planetary systems are windows into the deep past of cosmic world-building. Some planetary systems are more than 11 billion years old. When the Kepler 444 system was discovered, astronomers realized that planets had been forming for most of the universe's history. At 11 billion years old, this system predates our solar system by over 6 billion years, meaning that worlds existed around other stars when our Sun had not yet begun to form. The planets of Kepler 444 are all smaller than Earth and orbit very close to their star, completing their orbits in just a few days. Whether these ancient worlds could have ever supported life is unknown, but their existence proves that the ingredients for planet formation were present in the early universe. Other old systems may be discovered as surveys continue, revealing more about the early history of planetary populations. The galaxy may contain countless ancient worlds that have persisted through billions of years of cosmic evolution. These elder planets are reminders of the vast timescales over which planetary systems exist. Planets have even been found in the crowded nurseries where stars are born. Star-forming regions like the Orion Nebula are chaotic environments filled with young stars, dense gas clouds, and intense radiation, yet planets form even in these tumultuous cradles. Protoplanetary disks have been imaged around young stars still embedded in their birth clouds, showing that planet formation begins almost immediately after stellar ignition. These nascent planetary systems must contend with the gravitational influences of nearby stars, the erosive effects of intense ultraviolet radiation, and the turbulent dynamics of the star-forming environment. Some disks are truncated by close encounters, while others are photo-evaporated by radiation from massive nearby stars. Yet despite these challenges, planets clearly do form and survive, eventually escaping the crowded nursery as their host stars drift apart over millions of years. Studying planets in star-forming regions reveals the earliest stages of planetary system assembly. Every star that eventually wanders into the galactic field carries with it the planetary heritage of its birth environment. We have discovered thousands of exoplanets in just a few decades. The first confirmed exoplanet around a Sun-like star was discovered in 1995, and in the 3 decades since, the field has transformed from a speculative frontier to a mature science with thousands of confirmed worlds. As of now, over 5,000 exoplanets have been confirmed, with thousands more candidates awaiting verification. This extraordinary pace of discovery shows no signs of slowing, with new missions and improved techniques adding to the count every year. Each discovered planet contributes to our statistical understanding of how common different types of worlds are, revealing patterns and populations we could not have imagined just a generation ago. The diversity of planets found, from hellish lava worlds to potential ocean planets to systems utterly unlike our own, has expanded our conception of what is possible in planetary science. What was once science fiction is now catalog science. The golden age of exoplanet discovery is only beginning. Every new discovery reminds us how strange the universe can be. If exoplanet science has taught us anything, it is that our expectations are frequently inadequate to the reality of what exists beyond our solar system. Hot Jupiters were not predicted before they were discovered, neither were super-Earths, puffy planets, retrograde orbits, or many other phenomena now known to be common. Each surprising discovery has required revision of our theories and models, pushing us toward a more complete understanding of planetary physics. The universe continually presents configurations we had not imagined, humbling our assumptions about what should be possible. This pattern of expectation and surprise is likely to continue as we probe more deeply into the planetary populations of the galaxy. The history of exoplanet science is a history of wonder, with nature consistently proving more creative than our imaginations. Strangeness is a feature, not a bug, of cosmic exploration. There may be more planets than stars in the Milky Way. Statistical analyses of exoplanet detection suggest that planets are ubiquitous, with most stars hosting at least one, and many hosting multiple worlds. If these estimates are correct, the Milky Way alone may contain hundreds of billions of planets, potentially outnumbering the stars themselves. This abundance transforms our understanding of the galaxy from a collection of stars to a vast archipelago of worlds, most of which we have not yet glimpsed. The sheer number of planets implies that even rare types of worlds, those with unusual compositions, orbital configurations, or habitability conditions, must exist in enormous quantities somewhere in the galaxy. With so many planets, the probability that at least some host conditions favorable to life becomes correspondingly higher. We are not merely searching for a needle in a haystack, we are searching a field containing countless haystacks, each with its own potential treasures. The galaxy is a planet factory, and we are only beginning to count its products. We are building telescopes to image these worlds directly. The next generation of astronomical instruments aims to achieve what has so far been nearly impossible: capturing direct images and spectra of Earth-like planets around nearby stars. Proposed missions like the Habitable Worlds Observatory would use massive space-based coronagraphs to block starlight and reveal the faint glow of orbiting planets. Ground-based extremely large telescopes, with mirrors tens of meters across, will use adaptive optics to achieve similar goals for closer targets. These future observatories will not merely detect planets but will characterize them in detail, measuring atmospheric compositions, identifying surface features, and potentially detecting signs of life. The technical challenges are enormous, requiring precision optics, stable spacecraft, and advanced data processing, but the scientific payoff would be revolutionary. Within the next few decades, we may have images of pale blue dots orbiting distant suns, other Earths that will become individual destinations in our cosmic exploration. The dream of seeing other habitable worlds is coming within reach. Somewhere out there, a planet like Earth might be quietly waiting. Among the billions of planets in our galaxy, it seems almost inevitable that some closely resemble our own world. Rocky planets with liquid water oceans, temperate climates, and active geological cycles may orbit quiet stars in benign regions of the galaxy, harboring conditions suitable for life as we know it. These Earth analogues remain largely undiscovered, too small and too distant for current technology to detect reliably, but statistical arguments strongly suggest they exist. One of them might already harbor life, perhaps intelligent life, that looks up at its own night sky and wonders whether anyone else is out there. The search for Earth's cousins is one of the most profound quests in human history, touching on questions of our origins, our uniqueness, and our place in the cosmos. Somewhere among the countless stars visible on a clear night, one may warm a world not so different from our own. That world is quietly waiting for us to find it, a distant sibling in the vast family of planets orbiting through the gentle darkness of the galaxy. And now the quiet wonders of distant worlds begin to gently fade into the stillness of the night. You have wandered through over 100 peaceful truths about the planets beyond our sun. From ultra-hot Jupiters with iron rain, to frozen rogues drifting alone through the void. From diamond worlds and water oceans, to planets orbiting twin suns in skies we can only imagine. You have explored worlds where glass falls from burning skies. You have drifted past oceans deeper than any mountain is tall. You have met giants larger than Jupiter, and wanderers untethered to any star. You are part of this story. The atoms in your body, were forged in stars that may have hosted their own planets. The same laws of gravity and chemistry that shape those distant worlds are at work within you right now, holding you together, keeping you alive. You are stardust contemplating stardust. If your eyes feel heavy now, let them close. Let the rhythm of your breath become steady, like the slow orbit of a distant world, like the patient turning of planets that have circled their stars for billions of years. Tonight, as you rest, the universe continues its quiet work. Planets are forming in distant nebulae. Stars are being born and dying. Somewhere in the darkness, worlds we have not yet discovered are quietly spinning, waiting to be found. You are a small, warm presence within this vast cosmic ocean, peacefully resting among the wonders. Sleep well. Sweet dreams. And may you carry with you the quiet knowledge that the universe is endlessly creative, and every distant world adds a new chapter to the grand tale of what is possible, a story that will continue long after the last thought of the day has faded into peaceful darkness. Thank you for joining me on this journey through the worlds beyond our sun. If you enjoyed this video, please subscribe to Drowsy Discovery for more soothing explorations of our remarkable cosmos. There are more wonders waiting. More secrets hidden in distant skies. More gentle truths to drift through on quiet evenings. Rest well. And may the quiet turning of distant planets keep you company through the night. This has been Drowsy Discovery. Good night.